Again, welcome to, I think this is lab 10 for physics 11. We have quite a few topics to cover today. And actually this time around is slightly different. For one thing, the lab is not due next week, this lab, okay? It's due in 2 weeks. So it's not November, what is it? November 6th is the next Friday? Come on. So November 6th is next Friday, but this is not due November 6th. This is due November 13th, okay? So not this coming Friday, the Friday after. So that's when this lab is due. And the reason why is because you really have two options for this lab. Option one, to do the report for this lab and be done with it. And that includes a portion that I did not give you yet, okay, pertaining to the motor. And option two is actually not to do this lab report completely, okay? You opt out of it, provided you do the last activity in it, which is the motor. You build yourself a motor. If you do that, if you opt out of the this lab and you build the motor, you're actually also exempt from the final. So you're not going to take the final for this class. The final for this class would be included with the lab for the grade, for this lab, basically for this report. So I hope that it's going to be clearer as we go through these details. Now, if you choose to do the report, that means this lab will be counted for you. And also, you will be required to come to the final, otherwise you're going to get a 0 in the final. So you don't want to do that. So that's basically how this thing works. Do you guys understand? At least the ones who are here?
Yep.
Yeah, you will have labs. We are not done with the labs. You still have labs next week. We'll have lab on Thursday, a week from today, lab 11. I think it's about the reflections. And we have another one after that. And we have a third one after that, after Thanksgiving or just around Thanksgiving. So we still have 3 more labs actually to do and do also the review for the final. So we still have all of the things as scheduled on the syllabus. So nothing has changed as far as that. The only thing that has changed is for this lab report is not going to be due next week on Friday. That is to give you time basically to research the materials needed and to see if you can do successfully the motor. If you can do successfully motor, you're going to send me a report back basically with one thing checked, saying that you're not going to do this lab report, rather you're going to do the motor. Okay, in which case the date is set already after Thanksgiving, where we meet in here and you're going to demo your motor, and you're going to actually upload also a video on how you built it. And that's the end of it. Then you're done with this class basically as far as the final, unless, I mean, that's it. I mean, you don't have to come to the final. You're done with this class. Now, if you opt out of this, I mean, you still want to do the report for this lab. Okay, you don't have to do you don't have to build the motor, but you still have to report on it, okay, and how the motor basically functions, and also do the other rest of the activities in this lab, which involve the magnetic field, okay, and also do the rest of the other labs too, as prescribed. Come time for the day of the review, you're going to be here for the review and also watching other people do the demo for their own labs. And also you're required to attend the final and take the final. Does this make sense? Do you guys understand what I'm saying?
So we would just have to do the last part for, if we wanted to do the motor, we just have to be responsible for the last part and not do the full lab, right?
Not even the last part. The last part basically is just the instructions. In a sense, you're going to just say, okay, I'm going to go through the details of the lab. Yeah. Basically, you're saying, okay, I'm going to build this lab, okay? I'm going to build this. I'm going to build this motor, okay? I'm sorry. I'm going to build this motor. And today I'm actually going to show you at least the version I did, okay? So that you guys have an idea of how this works, okay? And then that's it. That you're done with this lab report. So that's it. This lab will not count for you. Actually, basically, you're not going to get a 0 in it, but this lab basically will just count to your final, and you're excused from the final, and that's it. This is the class. You built your own lab. You did an activity. I would like to see how you built it, and you actually have to demo it, how it works, that it's working, and come to class time, you're going to basically go on Canvas and tell us how this works, and you're done. And you'll be given, depending on how many of you are going to enter, you're going to be given anywhere between 5 to 10 minutes, basically a quick presentation of that during on, I think, what is it, the 3rd of December or something like that. And that's the end of it. And then see you in another life, probably, if you're going to take Physics 10 with another physics class with me, or astronomy class or something like that. Okay? So that's basically in a nutshell what this lab is all about. So let's get into the instructions of the lab so that we see things, first of all, how they work. Let me go back into make sure I don't have anything that is not supposed to be. And let me go to the modules, open lab 10. Lab 10 is actually Physics 10. And let me share with you the screen. Don't be fooled with the points right now. It says 58 points. They are not 58 points, because for the same reason, this lab is still kind of, I did not really put any, so let me first of all share with you the screen. This is not the total points for the lab. Actually, you know exactly how this lab is going to be graded. Okay, any lab, as a matter of fact, how it's going to be graded. You will get 1 point for the your name, or missing it. Okay, you're going to miss that point. You're also going to have a 3 points for the abstract always, 5 points for the conclusion, 2 points for the questions, each question. Each cell in every table, and there are 2 tables in here, is worth 1 point. So a table, for example, of 4 cells will be worth 4 points. Table that has, for example, 24 cells will have 24 points. Okay. And then there is an extra thing in this case in here. There are 2 things. First of all, there is a graph that you're going to require to do, which is worth 6 points, as usually. Points will be deducted for labeling the axis. Points will be deducted for, or not labeling the axis, I should say, both of them, the X and the Y axis, not having the thing drawn to scale. And also that is another point where you can lose graphs. And also you're going to lose points for actually not representing the data, all of the data on the graph that you have on the tables. And you're going to miss points actually if you don't draw it correctly. So that's basically how this, out of 6 points, if you get everything correct, you get 6 points. You miss 1, you get 4 points. And if you miss all of them, you get 0 points. So there is a graph in this lab report. There is also a drawing of the magnetic field for different configuration of different magnets. Now you will each drawing is worth 2 points, and there are several of them. Okay, there are quite a few of them. So the points basically have to label the North Pole and the South Pole correctly, and you have to indicate the magnetic field with the proper arrows coming from the North Pole to the South Pole. So that's basically how the whole thing is. Okay, we're going to talk about that. I'm going to show you exactly what I mean by that. If you do that, and then you're going to describe the motor, which has its own points, it's going to be worth, I believe, how much is it? I think 25 points, the whole report for the motor, and you're done with it. You're gone. You don't have anything else. Okay, you're going to describe torques. You're going to describe energy involved with that. So you do that. Okay, so this is one version of the lab report. This is one way of doing it. The other way, like I said, the other rubric. So that's one rubric. Okay, that's one way of getting graded. So that I didn't put the rubrics because Canvas does not allow me for telling me, okay, you have one rubric A, a rubric B, and choose one or the other when you're grading. So it tells me only one rubric. So I didn't put it in here because I'm kind of constrained by Canvas. The second rubric will focus mainly on the presentation that you're going to do, plus the building, the construction of the motor, and showing understanding, and having neat presentation of your motor, and having it run at least for about I think a minute or something like that, continuously non-stop, and that's it. Okay, So that is basically how it is. The only reason why I'm not requiring it, sometimes when we were face-to-face, I require it, is because I don't know how much access to materials you have. That's why I cannot require it for you, because you may not have access to everything, okay? Some other things you should have access to, like, for example, paper clips. Things like batteries, we should be able to grab batteries, okay? That's easy. But a battery holder, you don't need a battery holder, actually. I'll show you a trick on how to do it without a battery holder. These things are kind of tricky. The wires, you have to really get some wires from some place that sells them, and it's not Home Depot or Lowe's, because I tried them and I ended up with this wire. This is the smallest wire they sell in Home Depot, and this is gauge 20. Gauge 20 is too thick for the purpose of this lab. You need a higher gauge. This is actually gauge 28, okay? This is light enough to do this. This is what is known as a alternator wire. Okay, so this would work fine for the purpose of the lab. Gauge 32 would be too thin, thinner than this. Okay, gauge 32 also would work. I think gauge 28 is perfect for this lab if you can get your hands on it. Okay, I bought a whole spool. If you guys had if you were able to meet in person, or I don't know how. I already asked the dean yesterday. We were in a meeting. Is there a way for me to basically give my students at least a meter long of this, each person? And he said probably we cannot accommodate it now, maybe for the next semester, because I will be doing this class again next semester. So maybe next semester is going to have. So this I got it from Amazon. Actually, as you can I get this thing in here? I don't know. Camera. Does the camera zoom on this thing in here? No, bad camera. Trying to get you to read this number in here. This number in here. That's the one that is marked. That's actually says 28 gauge. Okay, 28 to be more specific. AWG. That's the standard for it. Okay, you might get it cheaper. And if you know somebody who does these things, like somebody who works on alternators, and there are all kinds of shops in town, they might give you a free thing in there. Okay. And if I happen to be not too far from where you are, I'll be more than happy to give you a meter or 2 meters of this, what I have in here. You'll also need magnets, okay? This is the magnet I'm gonna be using, okay? This is rated at about 400 Gauss, okay? The strength of this magnetic field is 400 Gauss, okay? Gauss is a very, very basically common unit used for the magnetic field. Again, if I were to meet with you, I have these magnets in here. All of this are magnets. When we do this live in class, I share with them my magnets, and the students at the end give me back the magnets when they're done with them, and they build their own motors. Again, I talked to him about this yesterday in the meeting, and he said we'd be more than happy to basically make kits next time around and share them with the students. Okay, so those are the materials you'll need basically for the last part of the lab, for what you will need for the end of the lab. So let's get into the report, the lab report, and talk about the first portion first and see how that works. Let me first of all get your class. This is Physics 11. To find the right folder for it. I can grab it from here, Physics 11. Labs, Lab 10, and Lab 10 report form. Where is it? Form. Okay, so let me share with you that file. So first of all, don't forget your name. In either case, you have to do your name. Okay, I need to know who you are, who basically submitted the lab report. So that is a must, regardless of whether or not you're doing the building the motor or not. Okay. This is the general introduction of the electric field and the magnetic field, because this lab was intended actually for both of them initially, okay? But they look similar. Actually, the magnetic field looks like that of the electric field for a dipole, electrical dipole. Electrical dipole, what it is two same charges, okay? In magnitude, but opposite in sign. So for example, this could be a positive charge and this could be a negative charge. So the electric field in this situation is this lines, the solid lines as you see them. The solid lines are the electric field, okay, and they bend in this fashion. And they always emanate, they come, they leave the positive charge and they end up in the negative charge. Where is my pen? So they always leave from here, if this is where it's positive, okay? So if this were positive charge, then the field lines are this, ending in here, okay? This is a negative charge, assuming, okay? So that is the field lines, the ones that you see them in solid lines. And that's exactly how also the magnetic field lines also do, except I don't have a positive charge and a negative charge. I have a north and I have a south, okay? Every magnet has a north and a south. This is a horseshoe magnet, okay? As you can clearly see, it's actually labeled. The red one is north. The blue one is south, okay? So that is how they are labeled, okay? So this is the blue side, this is the red side, this is the north side, this is the south side. So this is a horseshoe magnet. It asks you in the lab instructions to talk about cylindrical shaped magnets, but I don't have a cylindrical shaped magnet in here. I have a bar magnet, similar to the one that is coming in the activities. So again, this has a north, this is a south. If I cut them in here in half, for example, I go in the middle and try to isolate north and south, I can't. I will end up with two magnets, one for north and south, and another magnet with north and south. So in other words, magnets behave like exactly the electrical dipole, always comes in pairs. It doesn't come in singles, which is the item number 1 for the discussion today for Physics 11. So magnets always are paired. Does this make sense to you guys? And like charges, you can have a positive charge by itself and a negative charge by itself. You can always carry, for example, when we did the demo earlier today for Physics 10, if you guys remember it, when I had the balloon, which I don't know what happened to it, okay? And I was able to rub it against the fleece jacket. I was able to put charges on it. Those charges actually have a specific sign, okay? They're positive charges in this case, okay? Whereas in this case in here, I cannot do that for a magnet. I also have a different kind of magnet in here, if I can find it. This magnet is actually a disc-like magnet. It's one side is north and the other side is south, okay? And this is similar magnets, except that I'm placing different kinds in here, okay? As I move them, actually I feel the interaction of the two, okay? So that is because I'm trying to push them against one another. Now I have positive and positive and negative and negative. I have actually negative and negative now, and not negative and negative, south and south, and now I have north and north, okay? So those are magnets. Every person who is familiar with magnets, basically who played with magnets, and everybody I assume of you also did that, have all kinds of magnets in here. This is actually a magnet too, okay? Case in point, if I take a metal in here, is a metal, it should stick to it. So that too is a magnet, similar to the other magnets I was showing you in here earlier.
Does that disc magnet also have a north and south?
Yes, this one also is a disc magnet. It has a north and south, except that these are super weak. I mean, I know you're not here with me to feel them, but they are super weak. Right now they're attached. If I take them and basically try to put them on the opposite side, they don't stay. Actually, I'm trying to keep it to stay. It doesn't. It has to, it flies actually, okay? Same thing, okay? So these ones are also paired to. All magnets, they cannot appear in nature as a single thing. In addition to this, magnets, there are the so-called electromagnets. This is an electromagnet. This is, right now, it's not a magnet at all. It doesn't attract metal at all. So right now, if I put metal next to it, or in here, it doesn't stick. Let me take the lighter material in here so that I can experiment with. So, right now, I have this paper clip, which is iron. It's supposed to be attracted to magnets. I have it from the other side, and it's falling. It's not being attracted whatsoever. If I take this one now and connect it to a battery, let me see if I can get some wires and connect it to a battery now. Okay. I don't want to have this long wire in here. How about this? Okay. This one. This wire is good. Let me see if I can get another wire. And this wire is good, okay? What I'm going to do now, I'm going to connect it to a battery, a 9-volt battery. So this is what we call an electromagnet, okay? Because it needs electricity for it to work. So right now, still it's not a magnet. The fact that I connected wires doesn't mean that it's magnetic. So right now, I'm putting the piece of iron, and it's still not being attracted whatsoever. However, I'm going to connect it to one end of this 9-volt battery. Let's see here if I can get it successfully to stick to it. No, it's not sticking. Where is the alligator clip? Where is the alligator wire? Okay, I'm going to do it with hand. Okay, so right now, I put my hand on it in here. Man, it's going to be hard, okay? Because I need 3 hands. So, can I? Okay, no, it did not stick. Oh, here it is. This is perfect, actually. This is actually for this purpose. See, I have a lot of toys in here. So now I have the battery ready. So instead of using that, I'm going to connect one of this here to it. So it's connected from one end, but it's still not an electromagnet yet until I connect the other end to it, okay? So here it is. So I'm going to connect it now. Now I should have a current now flowing through this. So now if I try the second experiment right now, let me see if I can get this higher up. If I take now this paper clip, I don't know if you see the end of it on the bottom, but it's there, okay? It's in here. It's being attracted. If I cut the current right now, it's going to fall. If I cut the current right now, it's going to fall. The reason why it's going to fall is because there is no current in here. This is an electromagnet. So when you have the current running through it, I know you can't feel it, but it's actually hot right now. It's warm because of the current that was running through it. So once you have a current running through it, it becomes an electromagnet. So this is different kinds of magnet. That's actually what you're going to be experimenting with it. This has a certain number of loops in here. As you can see, it's a lot of loops, so many turns in here, okay? Some of them are labeled, and you can read the label and tells you exactly how many turns in it. Some of them, like this one that I was experimenting with differently, does not have a fixed number of does not tell me how many turns it has, but this one also can act as an electromagnet, okay? So this is actually a big electromagnet too. And the magnetic field will be in the middle too. So this is also another kind of electromagnet. So there are 2 kinds of magnets. There are the permanent magnets, like this one. This is a permanent magnet. Or the ones that becomes magnetic only when you have an electric field. And, I'm sorry, when you have a current running through it. Okay, like connect them to a battery. So those are the 2 types of magnets that we're going to be talking about in this lab. So let's get into the activity in here. So the first discussion point is that magnets, whether electro or permanent, they always come in pairs. The fact that this one had a current running through it will make it so that the magnetic field also will run in a similar fashion, just like as if it's a normal magnet. In other words, it has a north pole and south pole too. Depending on how the current is flowing, if the current is going up, the magnetic field will curl around it, okay? So if the magnetic field is curling, is going around, if the current is curling, the magnetic field is going to be pointing upward. In other words, this becomes north and the other side becomes south, okay? So that is how an electromagnet also works, okay? It turns out actually even a permanent magnet has currents in it, except those currents they are canceling. Okay, this is the setting for doing it in the actual lab, but we're not. So the first question in here is, single isolated electric charges known as monopoles, like positive charge and negative charge, exist. As a matter of fact, for those sitting in physics 10, we have done it today. We took a balloon. I basically, first of all, I had to inflate it, and then I rub it against some material in there, and then I was able to attract charges. So I know it's charged, electrically charged. Okay, so I was able to isolate charges on the balloon, but you can't do that with a magnet. However, no magnetic monopoles are known to exist. We don't know if they exist. Okay, we cannot think of any experiment that right now show that they exist. They always seem to appear pairs. Magnetic charges can only exist in dipoles, similar to the one I was showing earlier in the picture, with the north always accompanied with the south. Why should they be the case? So again, the only reason why they are is because of currents. So when the current is going clockwise, counterclockwise, if I look at it from the top, it's actually going clockwise. So that's why it's always have in pairs. So that's the answer in a nutshell. Because the current, you can always, if it's going in one direction, you can always look at it in the opposite direction and see it flowing in the opposite direction. Okay. So
that doesn't occur with electrical.
Both, yeah, because even the permanent magnets actually have. Let me explain how the permanent magnets are, because materials for permanent magnets, and I know we didn't reach this point in lecture at all, and I don't know if some of you are actually taking classes somewhere else, did reach it or not. So let me illustrate what this thing is, at least with this picture here. Let's go to the slide.
We're still in sound and waves in my class, so we haven't gone.
Yeah, we're not there yet, too. Okay. So. Okay, so this is how, as I was explaining, if the current is going like this, okay, the magnetic field in this case is going to appear to be moving in this direction. So this is the magnetic field, which has a symbol B, by the way, in, symbolically. So this would be the north, the other side will be south. If I'm looking at it from a different perspective now, from the top, for example, I would see it going in the opposite direction, resulting in the north and the south always coming this way. Okay, so this is the north, this is the south. Okay, so it always have to do with the fact that the current actually has to circulate completely. So you always have them in pairs. In magnetic permanent magnet, so this will be an electromagnet. In a permanent magnet, though, iron, for example, this is iron, but it's not a permanent magnet. This is still iron, but it's not magnetized. This is probably, it's not iron, it's made out of nickel. Nickel also is magnetized, can be magnetized just like iron does. There's cobalt, which is even stronger magnets than the two. Okay, this is cobalt actually, which is a very, very strong, and it's I have to put it out in here, which is also, so there are three main materials that can be permanently magnetized, at least metals. There is cobalt, there is iron, and nickel. Is it nickel? I forgot which the third one is always, because it's not really okay. Ferromagnets. Yeah, nickel. I don't know the symbol for it. Is it Ni?
No, I think it's just N.
Okay. No, N is for the other one, for nitrogen. I think it's Ni. No? Is N for nitrogen?
Yes, N is for nitrogen.
Yeah, so Ni, I think, for nickel. Okay,
yeah.
So those are the three basically materials that can be magnetized. Okay, that can, at least the elements that can have become permanent magnets. Let's take one of them. It doesn't matter which one. Okay, and let's take a region of them. Those materials. Where I have a bunch of atoms. For example, 3 atoms. It's usually much more than that, but let's say, for example, 3 atoms. This is atom 1. Next to it, I'm just looking at the outer shells. Okay, atom 2, atom 3. And then I'm looking at actually on some sort of a structure where I have actually 3 by 3. Okay, usually if I'm looking at it as structure, it has to be 3 by 3 by 3. So it should be 9 actually, because it's three-dimensional, but I cannot draw three-dimensional. I'm drawing just a two-dimensional picture here. This region, if all the electrons happen to be moving in the same direction, so this is an electron, for example. Okay, and this is another electron, and this is another electron. So each atom has its own outer electron basically moving in one direction. This too also has its electron moving in the same direction. So if this electron is moving in this direction, and this electron is moving in the same direction, and this electron is moving in this direction, and this electron is moving, all of them, I have them moving in counterclockwise. All of them moving actually in the same direction, counterclockwise. The clock goes back, this one are going against the clock, all of them. So if this region of space are all moving counterclockwise, including the inner one, by the way.
Right.
What happened in this point in here? This electron is moving this way, and this electron is moving this way, so they cancel. And here they cancel actually its effects. When a charge moves, it creates a current. So these two currents cancel. So there is actually no current in this point in here. There is no current in here too, because this electron is moving this way, counterclockwise, and the other one actually is moving counterclockwise, resulting in two currents canceling one another. The current in here also cancel. Wherever they join, they cancel. Everywhere they join, they cancel, because the currents where they meet, they're opposite directions. This one is going counterclockwise, and this one is counterclockwise. Now, the outer region, though, it looks like there is a net current, because this current electron is moving this way, this one is moving also in the same direction, this one is moving in the same direction, as if the entire region, domain actually of this region, has a net current moving counterclockwise. Yeah. So this net region will result as if it has a magnetic field now. So this region now of the material, of any of these permanent magnets, look like this. So I have regions now. This region, for example, has a net magnetic field pointing this way. Another region next to it has a magnetic region pointing this way. Another region, for example, pointing this way. So I have different regions in space. They're pointing in different markings, okay? On average, when the material is not magnetic, everything cancel everything, okay? All domains, they're random directions, so they average to nothing. They don't have a magnet, just like this material in here, this iron in here. But sometimes, if you magnetize them, they actually stay more or less in the same direction. So they go like this. So this one is, for example, going this way. This one is going this way. This one, for example, is going slightly this way, probably off a little bit, but more or less, they are in the same direction. This one probably like this. So the material now becomes magnetized and has a net, which is the sum of everything, magnetization that is pointing in one direction. So it becomes a magnet, magnetized. So some of the materials, they do that by leaning on each other. One region is trying to align itself with the next neighbor, and the other one is trying to align itself with the previous one. So they help one another, if you wish. And this is actually, there is a solution that is called the self-consistent solution. So some materials, they seem to do that, and those are the ferromagnets, okay? Including iron, nickel, and cobalt, and some other compounds, okay? So you can have them magnetized, basically, so that they lean on each other. So in actuality, my point in here is actually still current, but on the atomic level. So there is a current in here too, okay? On the atomic level.
Yeah.
But I'm feeling it right now. It's in my hands. I don't feel that. I mean, I don't feel the charges moving around, because they're moving on very, very small regions called domains. So this is a domain, actually. Okay. So
the 3 by 3 would be the domain?
Yeah, the whole region, actually, a big chunk of the material has the same magnetism, but they're so microscopic. Now, if you take a magnet, and you put it under a material like iron, for example, and you put it under a very, very strong magnetic field, you're going to magnetize it by having more and more regions, basically. So this is the applied field. So this is an external magnetic field. And what you do in this case, you magnetize it. You're going to build it more and more until all the fields are aligned. Once all of the regions are aligned, you cannot align more, because you don't have more regions. So this is the maximum you're going to reach. You reach a saturation in this point.
No more domains, right, to magnetize?
Yeah, that's it. You reach the saturation. So even though you apply super strong magnetic field, but that's it.
Right.
The material says enough. I'm saturated. But then what happened was, when you reverse the sign, when you start to lower the applied field, you're going to reverse those regions, and to some point they cancel. Now this becomes N-magnetized, and if you keep on changing the direction, now actually it's going to be magnetized in the opposite direction. Okay. So it's
Clockwise
going
or
to flip
counterclockwise.
north, becomes south, and south becomes north. But again, because you only have a limited number of them, you're going to reach a saturation. And if you reverse it one more time, now you're going to actually go through the curve through this way. So you can play with this basically. Oops, why is this going forever and ever? I'm sorry. It's not supposed to go forever like this, okay? So once you have this, you can go back and forth. So the maximum is here, the minimum is here, and the region in between them. So that's why you use them actually for data storage in the old hard drive, HDD hard drives. I don't know if you guys heard of them. I mean, they were more popular than the SSD hard drives. They're cheaper actually. They use magnetic materials to store data in them, because all you have to do is basically apply magnetic field on the hard drive, and the magnetic field will align certain regions of the hard drive to a specific location. Now, when the spindle is running, and then you have the needle reading it, it's going to read the magnetic field in that region, and you can store values 0 and 1. Okay, that's it. And you have now digital information stored in an old hard drive, not the new ones that they use optical technology. So that's basically how the data storage is, and this curve has a name. They call it the hysteresis curve. The point being in here is, even permanent magnets actually, they are a result of currents, okay? In a self-consistent manner, the atoms helping one another to basically become in that direction, more or less, okay?
So
that's because Go ahead.
In order to magnetize them, you have to be able to point them all in a similar, that they're all helping each other out, going in a similar direction.
Yes, all of them more or less in the same direction, pointing together. Okay.
And to be able to do that, you would have to. You said you would have to apply a magnetic field to it, right?
You apply a magnetic field to it, or in some other processes that involve actually material basically moved around, like in the mountains, for example, that's where they form actually naturally, also with the with different processes. In places, for example, where for example in the core of the planet Earth, for example, we have a natural way of getting. That's why the Earth is magnetized, because actually what's going on in the Earth is we have it's superheated. And because of that, metals that are in it, which is mainly iron and nickel, actually, that's what the core of the Earth is. So because it's liquid, basically, these materials, and the Earth is spinning. It goes once around its axis in 24 hours. Now, basically, you have charges in motion. Because you have these metals, they have free electrons moving in them, so they start to move. So that creates a magnetic field for the Earth, and it's very important that we have that magnetic field, because it protects us from the solar radiations and from also the cosmic radiation that hits us on the Earth. So the Earth is a natural magnet. That's why this needle, magnetic compass, points always toward the north, because the north is actually the south magnetic field, okay, which is something that, and the geometrical north, where Alaska is and everybody is, that's actually the south pole of the Earth in terms of its magnetic field. And the south pole, the geographical south pole, is actually the north pole of the magnetic field of the Earth. So the currents are actually flowing in this fashion, okay? And that's why the magnetic field of the Earth is actually coming from south to north, and the needle, because it has this pointy direction, is pointing to the north, which is the south magnetic pole. So that is the Earth. The same thing is true for a lot of planets. Actually, they have this on their own. For example, Jupiter, and they have very strong magnetic fields. Some other stellar objects, like for example the magnetars and the neutron stars, they have actually the fact that they have neutrons in them, pure neutrons, and neutrons are super strong magnetic source of magnetism. So that's why they have actually tremendous amount of magnetism in there. So this is how magnetism occurs in nature. It occurs in nature through these processes, and also occurs in laboratory via electromagnets. Actually, in laboratories nowadays, you can achieve tremendous amounts of magnetic fields, strong, super strong. magnetic field, about the magnetic field is measured in Tesla, about 20-30 Teslas, which is a huge magnetic field. Okay, this value that I was talking to you about, 470 Gauss. Gauss is 1 Tesla is 10,000 Gausses. So this one is super weak compared to the ones that we achieve with electromagnets in laboratory.
So it's
Anyway,
like 1/40th of a Tesla, so it's not that powerful, right?
It's 1 over, what is it, 400 divided by 10,000? Yeah, that's typical number. It's strong. It's actually stronger than that of the Earth, because if I put it next to the
Oh, okay, I see.
the needle, yeah,
Oh,
the
wow.
needle,
Uh-huh.
yeah, it interacts with the needle. Okay.
Mm-hmm.
Yeah. So otherwise, when the needle on its own is going to go into the magnetic field of the Earth. So these things are strong. Actually, this one is worse. I can't even get it to come out.
Oh, wow.
This is a super strong magnetic field. So you can get hurt with these things. I had another one that was super strong. I mean, it hurt me in my hand because it flies into you. That's when you go to in MRI, they tell you to take all of the metals and everything else, because the MRI has tremendous amount of magnetic field too. Okay.
So the strength of that magnet, is it stronger because it's thicker, or is it stronger because of the material?
It's the material. It has strong magnetic field. It has strong magnetization inside of it. Super strong. Okay. That's. But again, these are nothing compared to what you do with this kind of magnets, with the electromagnets.
Right.
The electromagnets, you can control their strength, actually. Okay. So let's get back to the lab report, which is part of the lab report, understanding what magnets are, actually. Okay. So we're going to talk about the objectives in here. And then in here, this is field. Label the following permanent magnets and draw their magnetic fields. Okay. You need to tell me where is the north and where is the south. Remember, every one of them is worth 2 points. So the horseshoe magnet, similar to the one I showed you earlier. So you're going to label this one, for example, N for north, and this is S for south. And the magnetic field always leaves the north and goes to the south. Okay. In here, it's going to be straight lines. And in here, it's going to start to curve. Okay. Okay. Again, depending on where you labeled your north and south. Same thing. Now, this is a cylindrical bar magnet, but I don't have that in here. I have actually a bar magnet, okay, similar to it. So again, you're going to label a north and a south, okay, and draw the field lines, okay. Same thing. This is actually a cylindrical magnet, but you're looking at it from this cross section.
Would the cylindrical magnet, would those won't meet up in the middle, right? They're gonna have to go through the sides, through the ends.
It's either coming out or leaving, depending on your labeling.
Okay, so they're not. It's not going through the middle of the actual bar, right? It's going around like a.
Comes out of it. So we're gonna do a demo in here. We're gonna go through the lab, okay? So now I have 2 bar magnets basically, with their poles in the opposite directions. So north is facing south, and south is facing north. And in here, with the end-to-end opposite, meaning that north is facing north or south is facing south, however you choose your labeling. And the field line now should not, and here they should emanate from one and come to the other one, but in here they should not. They should repel one another. So you need to represent the field lines in here. And here you have 2 magnetic fields, but one next to the other, okay, with similar poles also. The north is next to the north and the south is next to the south. And in here, you have 2 bar magnets, again, identical, but one of them is the south is facing north and the north is facing south. These are disc magnets, so similar to the one I was showing you earlier, with the north, basically the red one from the top, and the field lines should be coming off of it and going around to go to the south, okay? And in here, I have 2 of them, similar to the 2 I showed you earlier, where you have actually a north from one side and south. This is actually labeled for you, okay? So you'll have a north and a south, and you're going to draw the field lines, okay? As they go to this side and as they go to the other side too of each other, okay? And in here, you're going to have the same 2 magnets, except now that you're looking at their north side. So the other side now is the south. So you need to be careful in how the field lines are. So the field lines ultimately will need to terminate in the south pole from the other side. but they should avoid each other in here. They should not go into one another from north to north. But in here, they can go to one another from north to south, okay? But in the same time, they can terminate in here, but there is other field lines that they are coming in here too. And other field lines that are coming from this north going to this south. So I hope that you guys take due diligence in here to draw these things perfectly. Every one of them is worth 2 points, so you have a total of 10 times 2, that's 20 points in here. Now we have this lab activity. So I'm going to click on it, and once I click on it, I'm going to take you there. So let me stop sharing that screen and share with you the screen that popped up. So you may need Java, not JavaScript, Java installed on your computer to see this one. If you have difficulty with it, please let me know, okay? Once it pops up, it's going to look like this. The first instruction tells you to put it at around 80%, okay? 82 is fine, okay? It left the compass. You don't really need to leave the compass, so I'm going to remove the compass for this demo, but you can leave it if you like. To show the field meter, you need that, okay? Now, you need to move the bar magnet to a position so that this little ones in here, this little compasses line up right in the middle. Try to put it next to it, okay? Not on top of it, but next to one of them. And try to center it around these two. I have one from this side, from the north side, and I have one from the south side. Okay, I'm going to count in here. I'm going to count 1, 2, 3, 4, 5. Those are the points I need to locate. Those have no units. They don't have a number like centimeter or meter or anything like that. They're just how many compasses you have moved, okay? I'm going to take this meter now and put it on the 5th one. This becomes -5, okay? I have to pay attention very closely to this number, BY. I have to get it exactly at 0, okay? Or at best as I can to 0. It's difficult. This is perfect now, okay? So BY is 0. BX is 1.01. B bar, that's the one I have to pay attention to. B bar. I don't care about BX, honestly. I don't care about anything. The only thing I want from this stuff is this thing in here has to be 0 Gauss. This one is 1.01 Gauss, which is basically as if it's not there at all, okay? Remember, I put the intensity to about 80%. 82% is good enough, okay? Now, I'm ready. So this is -5. I have 1, 2, 3, 4, 5. Anything from the South Pole is actually negative. Anything from the North Pole is going to be positive. So I'm going to read the value for -5. And I'm going to stop sharing this screen. And I'm going to go to my lab report and report the data in this table. So this is just the explanation of what I was talking about. Report this number in here. It's going to be 1.01, at least my data, okay? I hope you guys are not going to put 1.01 because you may have, first of all, different strength of the magnetic field and you may position it in different location. 1.01 Gauss, okay? So this is for a -5. Now I need to move a step back, a step closer now. And there are no units in here, okay? For the position. It's just how many basically compasses I'm moving it. So I'm going to go back into this screen, back to my where is it? Here? Yeah. I'm going to move it now to the -4 position. The -4 position should be somewhere in here. Again, I have to be very careful to get the 0 as much as I can. Here is a 0, okay? I got 1.8 now. So again, all I care about is the B bar, as long as I have a 0 in here for the BY, okay? So I'm going to stop sharing this screen, go back into my data file, and put 1.8 in here, 1.80. Okay? You guys understand what comes next, okay? Can anybody tell me what I'm going to do next? What is the next step? Anybody, any guess?
Sorry, can you repeat the question?
What is the next step? What should we do now? I already took 2 pieces of data from -5 when I was here, and now I moved it to -4, and I got 1.
Move it to -3 and keep the by at 0.
Does everybody understand what we're doing now? Everybody, I want to make sure everybody is comfortable with this thing here. I think you're right, Jose. Okay.
Yes, I agree with
Okay, pretty
Jose.
good. Okay, so you guys know how to finish this activity. Please do not report the data I have in here. Okay, it's your data will be different than this. Okay, so the next step is going to be here for -3, and then -2, and then -1. You don't need to do anything in here inside the magnet. Now we're going to move to the other side. Okay. All of these numbers are positive, by the way. These numbers are negative because I am on the left side of the magnet. I'm on the south side of the magnet. Now, when I move to the north side of the magnet, it's still positive. So let me stop sharing the screen and go with you to the other screen. I'm going to move this meter 1 unit. Right now it's 7. It's going to be hard when you are next to the magnet, okay, to get the 0, okay? So you're going to do your best. When you move it down, it becomes negative. So it's slightly... Is it? No, can't do that. Okay, guys, I'm going to rely on you. Otherwise, you're going to get an error. So this is the closest I'm going to read in here, 58.86, okay? That is 1 for the value of 1. So it's 58.86. So I'm going to come back in here and share with you the other screen and report the positive side in here, 58.86. Okay? Do you guys understand what comes next then in this table? What is the next step then? Come on, guys. I did 1 now. I moved 1 compass on the other side, on the North Pole. And I got the reading in here. And it's a positive number, by the way. All of these numbers should be positive. Because I'm looking at the B bar. I don't care about the sign. As a matter of fact, let me go back into it. Okay. It's giving me BX in here positive. And on this side, it should be... It's giving me also BX positive, which is kind of strange, okay? Now it's giving me a different number. Again, your numbers will not be the same as mine. So what's the next step now, after I got this reading? Where should I put it now?
Should go over 1.
Yeah, another compass, okay? So we're going to move to another compass and do the same reading. So this is, oh man, I got 0.5. Okay, this is as close as I can get it. 12.52 for the second position. So I'm going to stop sharing this screen, and I'm going back to the other screen and put 12.52. Okay, and continue. Does everybody understand what we're doing in here for this portion? Yes or no?
So are we just calculating the strength of the north and south?
No, we're going next to the north for 5 different positions, and we're going next to the south for 5 different positions. The strength of the magnetic field, yes, you're right, with that meter. And it's in Gauss, by the way. All of the readings are in Gauss. Okay? Yes? Everybody understand what we're doing or not?
If we're one compass away from the north and one compass away from the south, should they theoretically like be the same?
I don't know. You're going to tell me that.
Okay. All right, sounds good.
That's your job now.
All right.
Okay?
All right.
Okay, you're going to go to the link and test it yourself. Does this make sense to you guys? Everybody know what you're doing with this activity? Yes or no? I want to see at least a few more people who think that.
Yes.
Okay, Amanda thinks it's fine with her. Samantha thinks it's fine. Somebody else? Okay, I have more people now. Good. I feel better now. Good. So let me go back. I forgot to mention something very critical to this whole thing, okay? Let me delete this data because I don't want you to really honestly do this data because yours will most likely be different for several reasons. First of all, where you position your compass, and the second is the strength of the field. It's the strength of the magnet itself, okay? So I expect your data to be way different than mine. There is something I should have said in here before we even start this whole lab report. We should really answer this question. And I know I started saying it, and then for some reason I forgot to pick up on it. It's this thing in here, stop. Before starting this lab, you need to decide on how you want to proceed. You need to answer the choice question on page 11. So technically, I mean, we're going to go through the entire lab, but before you decide on doing all of this or not, you're going to come back to this page in here, 11, and you're going to click whether you prefer to build the motor or whether you prefer to do the report, okay? If you're going to do the report, then you leave it the way I marked it. If you're going to prefer build the lab, then you skip everything, except your name.
Will the things that we do in this lab, like the whole lab report, will we use that to build the motor? Like, is that like
No, we'll talk about that. It's just this section. Okay? Does this make sense to you guys? So before actually starting doing the lab report and deciding on it, obviously I need to know who you are to make sure that you write your name in there. Okay? And then the rest, you can skip the whole thing. All you have to do is just go to page 11. That's how actually I'm going to look at your report. First, I'm going to look at page 11, what you said on it, okay? If you click on this, then I will ignore everything, and hopefully you have ignored it too. If you're going to prefer report, then you're going to click on this one. Then I'm going to grade you on the everything, including this portion, by the way, because there is a portion in here, okay? So, which you will be getting to. So let me go back to where we were. As if we're doing this thing. So we discussed all of this so far, and we get the table working, okay? So we know how to get the data. Then what happens to the value of the magnetic field inside the bar magnet? Again, you're going to take the meter, and you're going to move it inside the bar magnet in here, and you're going to tell me what happened to the strength of the magnetic field in here. Is it fixed, constant? Is it changing? Is it changing too much? Is it changing too little? Or is it zero? Or is it changing? However you think about it, okay? So I want you to do that on your own, and you tell me what happened while we are inside the bar magnet with this meter. So you're going to move it in several places, 3, 4, 5 places, and note the magnetic field in there. Is it changing? Is it not changing? If it's changing, is it changing a lot or is it changing a little? Do you guys understand this question? Yes? Or no?
Yes.
Okay, very good. Okay, so let me go into the rest of the lab then. You're going to plot in this graph. The x-axis is going to be your position. Remember, it's arbitrary units. It's not meters or centimeters. It's basically compasses, the number of compasses, okay, roughly. And on the y-axis, it's going to be the strength of the magnetic field in Gauss, okay? So you need to scale your graph accordingly. What happened in here? Why is my PDF is not responding, man? Okay. So you're going to graph it, that data basically. Remember, everything is positive. The entire magnetic field in both regions is positive. So it may look kind of odd. It's not going to be a whole line. The origin has to be somewhere in the middle. It cannot be here either, because you have some negative values and some positive values. So the origin can be smack in the middle or one of these points in here. Remember that you have up to 5 units. So if you're going to put this one 1, this is 2, this is 3, this is 4, this is 5, that's fine, but it's going to end up in here. So you have to remember to scale your units correctly, okay? That's one thing. But the magnetic field should be something that is probably going to be like this, some sort of a triangle, okay? Some sort of a big head, okay? If it's a line, okay? If it's not a line, it's going to look strong in the middle near the magnet and weak away from the magnet, okay? So that is how you're going to graph it. Then based on your graph, what is the relationship between the magnetic field strength and the position? Not only that it increases or decreases, I want to know, is it linear or not linear? Does the magnetic field decrease as the distance increases linearly or quadratically, or what do you think, okay? So again, this is open to you in here. Based on your graph, you're going to look at it and see if you can do it. So that is question 3. Question 4 now, question 4. The second part is about electromagnets. So I'm going to stop sharing this screen with you guys, and I'm going to share with you the one has to do with the same where we were before. And I'm going to click on the second link, which is the electromagnet. Now, the electromagnet, it starts from the get-go. I don't really need the compass in here. I need the electrons to show, and I need also to show the same thing as we were showing it earlier. Again, I need to leave it at 4 from the beginning, and I'm going to position it closer somehow in here. And again, try to keep the value of the BY 0. The reason why this is better is because it gives you a way. Again, I'm having difficulty getting it 0. Okay, perfect, 0, okay? So at this point, what we're going to do in here, we're going to change the number of loops. How many loops? Remember, I told you that you have a number of turns in the electromagnet. So I'm going to change the number of turns to 1 turn, okay? And I'm going to read the strength of the magnetic field. It's telling me it's 22.22, okay? So I'm going to come in here, stop sharing the screen, and go into my PDF file, and come into this table. And for one loop, I'm going to put 22.22 Gauss, okay? Stop sharing this screen, go back into the second screen in here. Don't change now this, leave it where it is, okay? The only reason why you needed 4 to begin with is just to give you an idea where you position it. You don't want to position it inside the loops, slightly outside in front of the electromagnets. So now you're going to change the number of turns to 2 turns, as you can clearly see from this image. The strength of the magnetic field now is 44.4. So I need to report that in the table. That is, again, my data. Your data may be different, okay, because you may have positioned this one differently. And then the third one, now the third one, it's giving me 66.67. And now for 4 turns, it's giving me actually 88.89. So I'm going to report all of that data into my table in this side, in here. And based on that table, I'm going to answer this question. Based on your data above, does the strength of the magnetic field of an electromagnet increases or decreases as you increase the number of turns, as the number of turns increases? In going from 1 to 4, do you notice that the strength of the magnetic field goes up or down? Okay, this is an easy question. Now, for 4 loops, vary the strength of the battery and notice how the strength of the magnetic field changes with the voltage in the battery and the speed of the electrons and the circuit. How do you think the magnetic field depend on the current? What value of the voltage in the battery would give you 0 Gauss magnetic field? So this is your job now. So now keeping it at 4, we're not changing the 4, we're changing actually the voltage now. As we change the voltage, the current changes, and as the current changes, we will see actually the speed with which these electrons move. So with more voltage, there will be more current, the charges will move faster. With less voltage, the current will be less, and now the magnetic field will also be less, okay? At least according to this graph, and according to my data. Yours may be different, okay? Now, again, you're going to answer that question based on what you notice. And then, can you get 0 Gauss in here? What value of the current, which is basically the speed with which these electrons are moving, and also the voltage, would yield 0 magnetic field? Okay? In a sense, I did it earlier, basically, when I cut the current. So that should give me a 0, because the iron dropped from the electromagnet. Okay, so let's continue with this. Now comes to the last part of this lab, okay? You will build your own DC motor. There are many ways to build the DC motor. A way of making it is this. So go ahead and Google it if you like. Go to YouTube, see how people do it, okay? As I said before, actually the weekend I was trying to do mine. I went to Home Depot and I looked for the wire gauge. Actually, I didn't like the ones from Lowe's, so I went to Home Depot. I thought I have a good one. So I bought it. I bought a lot of, I think I bought 20 feet of wire. And this is basically how I built it. Tried to build the loop, okay? I have about 7 loops in here, okay? 7 turns. And I tried to run it with the 9-volt battery. It did not run at all, okay? If it does not run with a 9-volt battery, it will not run with a 1.5-volt battery. That is because this has tremendous inertia in it, tremendous gravity in it that keeps it from actually turning. So this one, on the other hand, the one I built afterwards, after I ordered the stuff so this is how you make it, okay? So let me make one quickly in front of you here. With a D4 battery, or any battery actually, any round shape, okay? I really don't want to remove it at this point. I'm going to show you later on, okay, after I run this thing in here. So this is the D4 battery cell.
Would you be able
this is
to,
a 1.5. Sorry?
Would you be able to unshare? Because I can't see your camera. I can't pin it either because oh, there we go. Now I could see him.
Okay. So this is basically the D4, this is the battery basically that I have in here. I happen to have a battery holder. This battery holder, you can actually order a bunch of them from Amazon. I think they have like 4 of them if you're interested. And they sell them for like $8. So if you really need just one, you probably don't want to do that. So another alternative, what you can do is actually use the tape. Because all you want actually is, where is my paper clip, because I need the paper clip to get this thing going, okay? So short of doing that, I'm going to actually have, this is one paper clip. When you get paper clips, try to get them of the same shape and the same size, okay? Don't get one of them big and one of them small. So I actually have both of them identical, okay? So I have both of them identical. So this is what I do usually for this purpose. So what I do in here, I open one of them. Okay, open both of them. Actually, I'm going to have them the same shape, and open it one more time. And on the other side, I'm going to basically flip it in such a way, turn it actually in such a way this is how it's going to look like, okay? This is how it's going to look like, okay? So this is one. I'm going to take it, because I have a nice battery holder in here, and it actually snaps in place in here. So I have this one ready to go, okay? This is ready to go. I'm going to have another one sticking from the other side, similar to this one. And I will have 2 that are ready basically to put my wire on it. So what is the other one? Was it this one? Oh, here. So again, I need another one. again. This is iron, by the way. This you need to go to your report, because if you're, I mean, the ones who are not choosing to write basically the to do the actual build, they need to report on how to make one and how this works too. Okay. The ones who are no, they can just explain it and they're done with it. Okay. So I have two my holders in here, both of them basically, as you can clearly see them, and I need to line them up closer to one another, actually, so that this thing will sit nicely on them. Oops. Where did it go? That's bad. Let me find it, okay? I know it fell in here. Did you guys see it? I don't want to make another one. Okay, that's not good. Here it is. I know it fell on the ground. Okay, it needs to be in some sort of a equilibrium position. So right now, there is a current actually flowing, but it's not going anywhere because actually I need the magnets for that, okay? Without a magnet, this will not work. So here is my magnet. Magnets usually sit fine on the battery because of the fact the battery has metals in it. Right now I have my magnet. I have my things in here. So this is my motor. You guys see it at work? Yes or no? Okay, let me show you what this loop is. The loop needs to be made out of a material that is coated. This is the material that I used for it, okay? It's coated. It's in other words, it's insulated. But from the ends, you need to shave it, okay? You can use actually sandpaper for it, but what I didn't use sandpaper because this is too thin for sandpaper. I kept on cutting it. So what I did actually, I used a knife, a sharp knife, okay? And I put it on the edge and was very careful with it, trying to shave this thing. So I put it actually on the edge of the desk and I kept on it very carefully. I removed all of the shavings in it because you need contact. You need contact with this thing in here. So this is what's going on in here so that we are all on the same page. So this is the positive side. As you can clearly see in here, it's positive, okay? So the electricity is coming from the positive going through the wire because this one is shaved, it's find connection. So it's going to go through the loop several times and that creates its own magnetic field. This becomes a magnet because it has a current now, it becomes an electromagnet. But it's next to a magnet. So it wants to turn to align itself with the external magnet. The minute it goes, the inertia will keep it moving and that's why it's going to turn and turn and turn and turn, okay? On the other side, now the charge will come in from the other side, or the electricity will come in from the other side and come back into here. So when it comes to here, the battery will force it back through it to come from the other end and keeps this current going and the battery is still running, okay? If you cut the connection, then in this case you lose the, but you need a magnet and you need the electromagnet to make how a motor works, okay? This is actually not called a magnet, this is a torque. The torque is actually due to, you require the torque in this case. The torque depends on how much current is flowing in the wires. And I have 4 turns actually for this one. And like this one where I did 7, this one is actually 4 turns. Oh no, there was another one that I did 7. I don't know what it is right now. The point being in here is that I have 4 turns. Remember from the experiment where you were changing the number of loops and finding different strength of magnetic fields? This is exactly what that means, okay? But now I have 4 times the current that is flowing in this loop which I can actually measure with a multimeter or estimate based on the type of wire. This is copper, and the length of the wire, which is, and also the gauge of the wire. So it gives me exactly how much current is flowing through it by finding the resistance, and I have the voltage, which is 1.5 volts. Then I know the current, then I know how much magnetic moment is in it. The magnetic moment is crossed with the actual magnetic field, will give me the torque necessary to get this one going. I had enough torque in here to overcome the gravitational torque, because this one, once it spins with the gravity, it should not go anywhere. It needs to overcome gravity to keep it running. Whereas for this case, it did not have enough electrical torque because the currents were so weak in it, okay? And this was too heavy, has tremendous gravity, so it did not overcome it. But this one, it was. Actually, I can try this one again and see if it works. At least it did not work before for me. So if it works, I'm going to be surprised. This is a 20 gauge wire that I bought from Home Depot. Okay, it's not going anywhere. It's the same thing, but it's not creating any kind of torque at all. So I try, but it doesn't go anywhere. It actually falls, and that's it. That's the end of it. And there is current actually flowing through this one, but when I measured it, it was too weak of a current to create a strong enough magnetic torque. Magnetic torque for the loop. Okay, so this is what you're supposed to be doing. You're supposed to do the following when you're trying to. Let me go back into the instructions. Okay, oops, I forgot to share with you. So this is basically what you need. You need this is one version of it, so you might have it differently, okay? So this version basically is you need 2 paper clips, okay? Preferably of the same type. You need a bar magnet, okay? You need a 1D cell battery. The 1D cell battery serves 2 purposes for me, at least, okay? It might not do the same thing. It will serve as a source for power, and it also will serve as a way of actually making this wire too. So this is basically what I do in this case. I'm gonna just take this portion in here. Again, you don't need this fancy stuff in here, okay? They have another type cutter in here somewhere. I had pliers in here somewhere. Okay, here they are. Okay, so it helps you basically to make the turns for you. So I'm making the turns, and here I'm counting 2 turns, 3 turns, 4 turns. That's good enough, okay? So I made 4 turns for this purpose in here. Take them, and now I have a loop, okay? The way you hold them in place is by running the wire along one side, and this is basically how you make it from one end. Again, you go to the other side, and you run the wire from the other side, and now you have the turn. And if somebody asks you what's the diameter of it, you know exactly what the diameter for this one is, just basically by either measuring the distance or just running a string around this battery, and now you have the exact diameter for this one, namely the radius. All you have to do now is shave this area from here and here. That's it, because this is ready to go now. Okay. So is this quick enough to do? The trick with it is the magnets. You need magnets, and you need this kind of wire, the thin wire. Okay. So if you have access to it, you're in great shape to do this. Okay. You need, okay, if you don't have a way to hold this one, you need either a rubber band, if you don't have the battery holder like the one I have right now here, or you don't want to invest in it from Amazon. What you can do actually too, you can get, electrical tape. Let me see if I have one in here. This one, okay? You can also put the wire around it, okay? Put the wire around it and run it throughout the battery, and that's it. That should hold it enough for you to demo the lab thing. So that is one way. So either a D-cell battery holder, or this thing, Or actually, I have seen it online when people use Play-Doh for it to hold the things with it, okay? So however you make it, it's up to you, okay? So now you're gonna document your steps. When you make the video, I wanna see your face in the video and you talking, okay? I don't want to have your uncle or your cousin or a person you know do it for you, okay? So if you want to have credit for it, you really have to show me that you, I mean, they can show you how it's done, that's fine. You can go to the people who build the alternators, and then they can give you actually the step-by-step on how to do it, okay? And that's fine, but as long as you do it yourself, I don't care, okay? As long as you yourself make your own motor and show me that it works, okay? Here are the steps. So the actual demonstration will be conducted after the Thanksgiving. So you're gonna upload the video for it, for how you made it, okay? And you're also going to tell us briefly in about 5 to 10 minutes how this thing works and what you did and so on and so forth in the class. Now, if you think you can't make it because of sound issues or something like that, we're going to play your recording, because you can have your phone, actually, you can record it with your phone if you like. Please try to make the recording as not too long, okay? No less than 15 minutes, but no more than half an hour, okay? So don't make it too basically this, and that's it, okay? Try to give it a little bit of explanation and time, like I was showing you in here how to make this one, okay? Now, if you prefer to do the lab, complete this lab report up to question 5. You will also be provided data for the DC motor and complete the supplement report. So you're going to be having actually different report that you're going to be doing based on your answer to this lab. When I see it, I will give you that, okay? So your conclusion needs to include all parts of this lab. You will be required to take the final exam if you opt for this version, okay? If you opt for this version, you will be exempt from the final exam because your grade for this one will go there and that's it. And usually, typically, if you have it working, you should not have a problem whatsoever. I mean, unless you have, unless you didn't actually build it yourself or something else, and that's another problem, okay? If you're into some difficulty also, you could get the most of the credit if you tell me exactly what went wrong. Like, for example, don't do this, okay? Do not get the 20 gauge wire because I already showed you that it's not gonna work, okay? Don't go to Home Depot and tell them, okay, I need the highest gauge because these things work backward, okay? A gauge 14 wire is actually gauge 14 wire is much thicker. Gauge 12 wire is even thicker than the 14. Gauge 18 is actually thinner than the 14, and gauge 20 is this one, okay? This is, they call it, what is it they call it for the, I forgot what the name for it. It's, I think for the bell, the ring bell, okay, wire. So that's how they call it there. But this is the highest number they have in Home Depot and also in Lowe's. So if you go to these two places, you're not going to be successful because it's not going to work. So do not try to do that and tell me the reason why I did not succeed because I got a higher gauge. I'm telling you from the get-go, you need 28 gauge or higher in ranking, okay? 28 gauge works perfectly, and it's actually ideal for the situation because it's thick enough so that you can have a grasp of it and it doesn't break on you when you're trying to shave it, okay? A 32 gauge might be too small. I did not try the 32 gauge. It may be too light, okay? It may not even sit on your properly, okay? You may need to hold it differently so that it sits on this two things, okay? But this one is heavy enough so that it sits on its own, and light enough so that the current in it is strong enough to generate the torque necessary for it to turn, to rotate, okay? Do you guys understand what's going on? So what was item number 1? Number one was the fact that there are no monopoles. Item 2, number 2 is that I need to know by November 13th whether or not you're doing one or the other. I assume that if you submit the report, that point, that's it, that's what you're doing. So when you submit your report, at that point, I know that you have decided to do one or the other, okay? So that is the second point. I'll make a decision by no later than November 13th on which one to do, Okay. The reason why I'm giving you 2 weeks, because it takes time probably to get your hands around some of these materials and get some information on how this thing works. Because honestly, I really prefer that you build the motor than you actually do the report. Because doing a report, we've been doing it for day one. That is something that is a given. So I assume that you guys have learned how to do that enough now. I'm hoping that you actually get your hands actually dirty, at least a little bit with these things. So I'm hoping for most of you to do this.
This will be like the actual first hands-on lab. Like
Okay.
I'm gonna make the motor, yeah.
Okay, so I'm glad
I agree
that
with
some
Amanda.
people, okay, I'm glad that some people are coming aboard. I mean, it's gonna cost you probably anywhere between $15 probably to $20 at most. But I'm hoping you get more out of it than that, in a sense that you learn something practical and how things work in practice. Now, I didn't demo something which is very important part of the process, and I don't want this to be part of your report. Okay, so do not go to Amazon or anywhere else and buy a pre-built motor. This is a pre-built motor, actually. Okay, and tell me, hey, I found one ready to go. No, that's not good enough. You have to build your own. So when I say build, you build. Don't bring me somebody else, okay? So I'm going to put it quickly in here. This is the battery that I was running, the 9-volt battery, okay? And I'm going to connect it quickly here. So I'm going to connect the red right now. As you can clearly see in here, where is my camera? You can clearly see right now it's not running. You will see it running quickly, okay? The minute I connect the other wire too, actually you can hear it too. This is stopped. This is running. So this is a motor. It's actually part of an Arduino kit that I have, okay? I have so many motors in here. There are a lot of them in here. I have another one where I forgot what it is. But the point being in here, do not bring the pre-built one, okay? That will disqualify you, so do not do that. You have to build your own, okay? So this is actually pre-built one for all kinds of electronics, for example, for robotics and things like this. And actually, any motor, you know, those things, for example, the fan in your house, the coffee mixer for the milk frother, or for example, the blender, or anything else is the same principle. It's the same idea as what we were doing. Any motor, including that of your car, the electrical cars, that is the same principle. Use electromagnets. A generator, though, the one that generates the power, where we get our electricity from at home, it's actually a reverse motor. It's a motor working backward, that's all. This one takes electrical energy, the motor, and converts it into mechanical energy, motion. That is what an electrical motor is. A generator takes mechanical energy and converts it into electrical energy. So that's backward, an inverse of that, okay? So those are the two fundamental things that you can see in any kind of power generation or basically power consumption, okay? So that's really the idea behind it. So I'm really trying to get you into these things, and I'm hoping, if not all of you, most of you will actually try to build your motor. Now, if it fails for some reason, okay, out of your control, okay, completely out of your control, and you did your best with it, you still can get full credit, or at least almost full credit, if you show good, basically, progress with it and things like that. And that still excuse you from the final, and you will not have a problem to worry about the grade for this class or anything else in terms of, at least for this part, for this this lab, okay? Now, like I said, do not go and try to use something that you know is going to fail and say, oh, did not work for me. No, that's not acceptable. You're going to be losing points on that, okay? So I'm telling you from the get-go, get the wire that is specifically designated for that. That is the key. The other key also is you need a magnet, okay? Once that is done, how you connect them, there are all kinds of ways, okay? There are many ways of doing it, including electrical tapes, including glue if you want to, okay? Including, when you connect them, try not to use a conducting materials, okay? I think I have some Play-Doh in here that looks like Play-Doh, but it is not. This is actually conducting materials. I got them from Chicago when we visited the national laboratory there with my students, actually. Oh man, with the engineering club when I was the engineering club advisor. So this looks like it's Play-Doh, and it's not, okay? It's actually conducting material, so you don't want this. So if you want to, you can technically use Play-Doh to connect the wire in there and have it in there. Actually, this flows too. And this is magnetic, actually responds to magnetic field too. So that is basically, in a nutshell, what this lab is all about. Yes? So we're not going to hold the session until 9:30 to 9:10 today. The reason why I'm doing that is because to give you ample time to start researching what you need to do, and hopefully come in 2 weeks from time. Now we still have lab next week, okay? And we have lab, and that lab will have the report also due on the same day, okay? The lab for the 6th is going to have its due. The lab for the 5th is going to be due on the 13th, okay? So we'll have 2 things due on the 13th. This one, where you make your decision, or the next one, of course, which is on the reflection.
So to make our decision, we have to mark that and then turn it in?
Yes, that's it. And
So
then I know you can, but I'm hoping that you gather information first before you commit, and then you discover down the road that no, I can do it. Okay, so it's I'd like you guys to think about it first, please. Okay, and what else I was going to say in here in terms of this lab in here. Yeah, the other thing also I would ask then, if you do that, I will send you basically when where to submit your video file. Okay, it's going to be on Canvas actually, and that's why I'm asking that it not to be too long, because if it's too long, then it may take you forever to upload. In which case, I will give you a link to probably a place where to upload it, or send it somewhere where we can actually have it, and then I can see it, and maybe we share it with the class and things like that.
And it was I saw up there it was 90 seconds, right? Or was that
90 seconds? I think 90 seconds for the operation of the thing in there. Okay, if it stays for 2 minutes, that's great. Okay. Now 90 seconds may be too much. Okay, so I may have to lower it down, because I have had problems in the past. I had students actually who lasted for several minutes, actually 5 or 7 minutes. Actually, we did this in different formats. One time, actually, what we did a competition who has the longest time just to keep it going. But at that time, they were using this, okay? So they had to actually hold it in place. And when you hold it in place, if it moves out or in, at least, what happened in this case, the magnetic field the torque becomes too weak for it to stay in motion, so you get tired and after that. But this one should last for a lot longer, so I expect there should not be a problem, okay? But if again that becomes an issue, but a minute is 60 seconds. I mean, a minimum is 60 seconds.
And then for the explanation, how long would you need the explanation for?
Basically, what I was saying, that what you're doing in this case, the magnetic field of the wire, or the and I can actually give you more verbiage on that, and you can actually Google these things, is the torque that is created trying to align itself with the magnetic field, but it's being actually slowed down by the fact that it has mass. So this torque must be strong enough compared to the gravity to overcome gravity, and that's basically how the motion keeps on going. As long as there is current, if you cut the current from it, then the whole thing stops. That's exactly what happened to a motor, for example. If you have the blender going, just turn off the button and there will be no more current going, and the motor stops in there and the blender stops. Okay. Same thing with this one I was showing you earlier. When I had the wires connected to the power source, okay, actually I can do it with this one. This is the negative side, this is the positive side, okay. It's kind of, it's trying to zoom on me. I don't want it to zoom on me. I want it to zoom on this motor. Okay. As long as there is current, there should be a power. That's exactly the same thing in here. If I connect it, there should be a power. Okay. This is an electric motor, but this is not the one I want you guys to do. This is the one that is pre-built. Okay. Actually, it has this legs in here to go on the Arduino board already. Okay. On the breadboard, okay, exactly ready to go. I was trying to show you guys earlier for physics 10 my diode. Was it physics 10? Yeah. And now I found it in there. See, A lot of junk in this place in here, a lot of garbage stuff. Okay, I hope you guys have had fun, like I usually do. Okay, it's kind of, sometimes I think about these people. Okay, I'm enjoying this thing very much, and I hope that the people who are going to watch this video later on, they will also make their decisions based on what they see. Okay, so there are two questions of the day. The first one is the fact that there are no monopoles. Okay, and the second one has to do with the fact that you're going to be making a decision for me on this reporting. Good? Can we stop the recording now? Did I miss anything? Okay, so I'm going to stop right now the recording. And like I said, we're not going to stay in session. The first one, Yontian, has to do with the monopoles. The fact, it's actually the first question. There are no magnetic monopoles, okay? They always come in pairs. Okay, so I'm going to stop the recording. And like I said, today we're not going to stay until 9:10 p.m. because I'm hoping that you guys will start thinking about what you're going to do about this report. And you still have 2 weeks to do it. Yes?